I'm from National Taiwan University, and it is an exciting moment to be here and share some information. And my topic is the piezoelectric two-mass damper that is designed for footbridges. The picture background is the example structure of today's presentation, and it is the Diode bridge in New Taipei City in Taiwan. And this is the outline. I'll first introduce the vibration serviceability problem of footbridges and solve this problem by piezoelectric two-mass damper, and then see an example structure that is in the actual world, the Diode bridge, and going to the conclusion. And I'll start by introducing the characteristics of footbridge. When designing footbridge, aesthetics concerns are emphasized, and there are two reasons why. First, footbridges mainly sustain pedestrian loads, and it is easier for engineers to design a more creative appearance. And second, footbridges are often located at scenic spots, schools, or other important locations in the cities. And because of the aesthetic concerns, footbridges are often designed as lightweight or long-span structures. Like the picture you can see, our example structure Diode bridge. But this kind of structure will bring low vibrational frequency and lowly damped behavior. And this behavior may cause some vibrational problem. And the vibration serviceability problems of footbridges. A man-induced vibration of frequency is proposed by Beckman and Amen that it falls in the range of 1.6 Hz to 2.4 Hz. And the vibrational frequency of footbridges often falls in this range. And the equivalent of two frequencies may cause resonance and further affect the serviceability. And we took one table from the French Structural Institute, FGC, and it classified 4 classes of comfort class: a maximum comfort class, mean, minimum, and when the acceleration is bigger than 2.5 Gauge, it is unacceptable for human beings. And to solve this problem, there are some common solutions: stiffening the footbridges or applying two-mass damper. And the concept of stiffening the footbridge is to enlarge the vibration frequency of footbridge, and we can avoid resonance. But on the other hand, it may also enlarge the section and the weight, and it will change the appearance of the footbridge, which is not what the designers expected. So in my case, I'll apply two-mass damper instead. And a two-mass damper is tuned to the natural frequency of the structure. And while the structure vibrates, the mass of the two-mass damper will also move drastically. So the damping device can dissipate the energy created by the motion of the mass. And there are mainly 2 ways to equip two-mass damper on structures. You can add it on the top floors of the skyscrapers, or you can suspend it on the below of the bridge. And there is an interesting question. Besides reducing the vibration, is there any possibilities that we can convert the vibrational energy into electricity? And so a new type of two-mass damper is proposed, the piezo TMD. And the concept is to add piezoelectric material into our conventional two-mass damper. As we can see, the piezoelectric disc can convert mechanical force into electricity. And some common material is the PZT. And there have been some models that is proposed by other engineers and scholars. And the main difference of the model in my presentation is that I put the piezoelectric stacks in series with the spring, so that we can get the maximum deformation and further get the maximum energy. So we'll take an example. This is the Diode bridge, and with the total span of 110 meters, with the width of 3 meters, and it starts up about 2016. And the vibrational frequency of Diode bridge is 2.32 Hz, and unfortunately, it falls in the range of the frequency of pedestrian loads. And the resonance makes the maximum of vertical acceleration to be 3.57, which is bigger than 2.5 scale, and it is unacceptable. And in the real world, it is actually placed a conventional 2-mass damper to reduce the vibration. And in my presentation, I will try to simulate using the piezoelectric 2-mass damper. And the yellow part is the piezoelectric stacks. And we set our design acceleration to be the average value of the mean comfort level class. So the number is 1.175K. And there are some simulations for the Diode bridge. First, we need the pedestrian load. And it is proposed by Central FGC that we can use a periodic loading with Gaussian distribution to represent the pedestrian load with the mean value of 2 Hz and a standard deviation of 0.2 Hz, like the GG. And we simplify the Diode bridge into a 1-degree freedom of structure with the mass and the frequency, stiffness, and the damping coefficients. So after we got the parameters, we can do the time history analysis. And the blue line represents the Diode bridge that is simplified as single degree of freedom. And the red line is the Diode bridge with conventional TMD. And in the blue line, in the acceleration, it is obvious that the peak acceleration is 3.57 and is bigger than 2.5 scale. And it is unacceptable. And the conventional TMD can both reduce the displacement and the acceleration effectively. And I'll go further to design the piezo TMD. And these are the parameters for the piezo stacks, the parameters for the circuits, and the mass. And we want to see if the conventional TMD and piezo TMD tune to the single degree of freedom. So we can see the frequencies are very alike. And also, when the single degree of freedom is applied to conventional TMD or piezo TMD, the equivalent damping ratios are larger. And we are going to check the acceleration after we analyze. In the frequency response, both the conventional and piezo TMD reduce the peak value of the acceleration. And the value we can see here, the peak value of the acceleration is reduced from 3.57 scale into 1.57 scale. And after comparing the acceleration, the main difference of piezoelectric 2-mass damper is the energy harvest. So we are more curious about this part. And conventional TMD dissipates most of the energy. But in piezo TMD, the input energy is 9.50 kilojoule, and the harvested energy is 7.12 kilojoule. And about 75% of energy are harvested. So we can go to the conclusion. First, the resonance of Footbridges enlarges the vertical acceleration, and it is proof that TMD can be used to efficiently solve this problem. And piezo TMD performs as well as conventional TMD at reducing structural vibration, but the piezo TMD further harvests the energy with high efficiency, while conventional TMD dissipates.